operating conditions are changing. So moral number one, or moral of the story, don't use pressures that are measured on the downstream side of a choke. In general, you want to use flowing pressures that are as close to the source as you can. What's the source? The source is the sand phase. If your flowing pressures are far, far away from the source, for example, plant inlet pressures or something way down at the delivery point, the accuracy or the reliability of your interpretation will be very, very suspect. Okay. Now I realize that in most cases we can't measure, it's not practical to measure pressures right at the sand phase. So we settle with measuring pressures at the tubing head or the casing. If you can get the quiet side measurement, in other words, the annular space between the tubing and the casing, in a well that does not have a packer in place, so we have a direct connection to the sand phase, that's better. That's an even better measurement than measuring on the tubing head side. But certainly we need it, if there's any choke or anything in place, we need it to be on the upstream side of that choke. So that diagnostic will tell you that right away. It's easy to see immediately whether rates and pressures are working for or against each other. Now again, there's other situations where maybe the data isn't measured this way. You might have daily production rates, but the pressures are only measured every week or every month. In that case, you wouldn't be able to do this diagnostic. So you may or may not have problems. Okay, so it's the diagnostics will really show you very quickly. It'll probably, if you're doing it properly, you'll probably end up with more questions than you had at the beginning. But certainly you need to investigate those things and make sure that you can make sense out of them. When the correct data were used in this case, as I found out later on that we had access to the tubing head pressures, but the field personnel didn't know what it was that we were looking for. So they sent the data, I suppose that was easiest to get access to, or the data that they thought that we wanted, which was the meter run data, where I actually wanted to put the tubing head pressures. Very clearly here it makes a huge difference, right? The tubing head pressures produce a clearly declining flowing pressure profile and completely changed the shape of the data. Now we're in boundary dominated flow, we only have 19 BCF. It dramatically changes the picture of the data. So if we hadn't done that investigation, we would have analyzed the data and come up with the wrong answer. The next step in this is to start looking at these sorts of diagnostics on log-log plots. And that's valuable for the same reason why it was valuable to look at data on log-log plots in the first place. We can learn a lot about the flow regimes and qualitatively what's going on in the data, because there's pattern recognition on a log-log plot that you just can't get on a linear plot of production data or pressure. For instance, this downward concavity that indicates boundary dominated flow is very clear on this plot. The upward concavity that indicates the transient flow is very clear. So we're going to start to see, if everything was perfect in a perfect world, all the data should fit really nicely somewhere on that curve. Well, in reality, that doesn't happen. So there's some diagnostics that go along with that that can explain what it is that's causing that. Now, this work was done, with these diagnostics was done a few years ago, I think in 2004, by myself and some colleagues at Phuket, and we wrote an SPE paper about these diagnostics. I want to start, we can categorize these things a little bit. I want to start with discussing what I call material balance diagnostics. And the reason I'm calling them material balance diagnostics is because they happen over a long period of time, way into the future in boundary-dominated flow. Okay? Maybe not in the future, but in a long-term data set where we have boundary-dominated flow. These are diagnostics that take a long time to develop and are happening slowly, diffusively through time. They're not the sorts of diagnostics where you watch day by day and say, oh, my pressure dropped, therefore something's happened. These are long-term, low-frequency type diagnostics that we're talking about. And they're actually very straightforward. If I have my unit slope, the unit slope represents volumetric depletion. So this is, again, and we talked about this before, this is the harmonic stem for constant rate solution. And in order to do this properly, I have to plot the normalized rate versus material balance time on these type curves. So it's just the same as a Blassingame style type curve. So I can simply take my Blassingame plot the data on there, and if I see the data matching on that unit slope, that means I've got volumetric depletion. There are really two options that it could do that's different from the unit slope. Right? One is that it could drop below, and the other one is that it could drift above. If it drifts above the unit slope, then that's an indication that I've got a reservoir with pressure support. So all of those cases that ARPS identified, such as multi-layer, solution gas, water drive systems, connected gas systems, composite systems, all of those sorts of things that can provide some sort of recharge over time are going to show data plotting out here, and you can do the diagnostics on this sort of plot, and it becomes very clear when you have systems that aren't volumetric. In other words, you're not draining a closed tank. You're draining a system that has some sort of influx on a boundary. So there's a boundary that surrounds this thing, and somewhere there's some fluid. We don't know what kind of fluid. We can only tell that there's an increase of energy somewhere occurring in that system. So we don't always know whether it's a water drive system, if it's a gas reservoir. Is it a water drive system, or is it gas that's recharging from a lower permeability gas system? We don't know that just by looking at this. We may need to use other information to evaluate that. On the other hand, if the data falls off the curve, that means we have a leaky reservoir. And leaky reservoir means interference. So that's where we have a situation where a well has been drilled in a volumetric reservoir, but later on another well gets drilled in that same reservoir, and so the available gas in place or oil in place for that first well is reduced. And that's our leaky reservoir. So both of these are very common. And the diagnostic is powerful because we can immediately identify whether that's occurring or not. We may suspect that there's interference somewhere, but if we don't see that diagnostic, then there's no reason to think that there is, or at least in a meaningful sort of way. Whereas if we see the diagnostic, then we know that there's something there. So what I'd like to do is show two examples of these things, one of each. So first of all, we will look at an example of pressure support. I spoke too soon. First of all, we will look at an example of a leaky reservoir. So this is our interference case. And this analysis was done entirely with public production data. So we made the assumption of constant pressures. We didn't have active flowing pressures. Normally, this would be a little bit dangerous because I've just finished telling you on several different, as part of several different discussions, that point pressures are very important. what the line pressure was. So we were able to predict the flowing pressures in this situation. In most cases, you want to have access to all those flowing pressures to get a more accurate interpretation. Now, in this example, we have 3 wells. It's a 3-well system. The first well came on production in late 1991, and then you can see there's a few years of production where nothing happens. And the blue curve indicates the aggregate production of the 3-well system. The red curve indicates the production just from well 1. So you have 2 instances where wells come on stream, and the aggregate production of the system is increased quite a lot. And you can actually see the production from well number 1 starting to fall off. If we go to the analysis and look at the Blasingame plot, the diagnostic becomes very clear. Okay, our unit slope is shown in blue, and the interference is immediately apparent because the data drops off that curve. So that's the diagnostic. We can immediately tell, yes, this well is being influenced by interference from the offset. What can we do about it? Well, there's some different things that we can do. Blasingame and his colleagues have proposed one method that we call multi-well analysis, and the multi-well analysis allows us to correct for that interference effect. And what that's actually doing is it's changing the material balance time function. If you recall, material balance time is total cumulative production divided by the flow rate, Q. What if I were to include the cumulative production for all 3 wells? So it's now going to be the sum of all of the cumulative production of 1, 2, and 3, and however many other wells I have that I want to include in that grouping. So by doing that, you can imagine all those data points are going to be shifted over because the cumulative volumes are higher for the grouping than they are for the single well. And the thought is that if I've included the proper combination of wells in that grouping, then I should get all the data to fall properly onto that curve. If I haven't included all the wells for the grouping, then it's not going to work. For example, if I go back to the well manager and remove well number 3, so I'm extracting well number 3 from that grouping. And now if I go back to the analysis page, you can see that there's a shift in the data, but it doesn't go far enough now. Okay, so the multi-well is being invoked here, but there isn't enough cumulative production to account for the shortfall that's observed in the production data as it falls off that curve. By the same token, if I put extra wells in there that didn't belong, the data would overbelong. So there's the right combination of wells that will imply a completely closed system. And that's the solution that I'm looking for. And that will help me establish what the total gas in place is for that entire system of wells in that multi-well system. All right, let's look at the other example. And the other example is the pressure support. This is a very different reservoir. This is a high-pressure, deep gas condensate reservoir in the Gulf of Mexico. As you can see, we have very high production rates. It's gas condensate, and during this producing portion of the data, we have really no water production at all. But we suspect that this might be a water drive system because some of the offsets have watered out. When we look at the analysis, and look at the Blasingame type curve, the effect here is a little more subtle, but it's unmistakable if you zoom into it and really take a closer look. Okay, so it starts down the path of a unit slope, but then starts to depart, and that indicates the pressure support. So the pressure support is clear from here. What is it that's causing the pressure support? We don't know. There's not enough information here to tell me whether this is a water drive system or a connected gas system. Okay, but I do know that there's some additional energy that's coming into play here that's causing this pressure support. Now, I suspect that it's, as I mentioned before, I suspect that it's water drive because some of the offsets have watered out. That's why it is so important, so critically important to have an understanding of the whole field and not just look at production data in a vacuum. Because otherwise we wouldn't be able to make that connection and say, okay, this is what I think is going on. So what I've done here, you can see the data snapped into place. That's because I've already done the analysis, so I'm going to remove the analysis. But what I've done here is a pseudo-steady state water drive analysis. And the pseudo-steady state analysis is going to take the data and basically subtract the water drive effect to try and collapse the data back down onto the stem. It's pretty much the inverse or the exact opposite of what the multi-well model does. The multi-well model adds cumulative production to try and get the shortfall taken care of. The water drive is going to eliminate energy to try and get it collapse back down onto the stem in the opposite direction. And in the water drive system model, what we do is we can interpret initial water in place volume to an aquifer productivity index. And by fine-tuning those 2 parameters, we hope to get the best possible match of the data. So the way this works is I can increase the volume, and you'll notice that I can increase the volume. I'm not sure what happened there. Let's make that number big. I can increase the volume a whole lot. And in fact, right now I've got 713 million barrels there, and nothing's happened. And the reason nothing's happened is because my aquifer productivity index is a little too small. So I start to increase my aquifer productivity index, and hopefully I'll start to see an effect in the data at some point in time, and I can get the right sort of combination of parameters here to match that data. Now, it's probably still going to be some non-uniqueness. The initial water in place is quite high here. Let's try and lower it and see if it makes a difference. And obviously I can lower it quite a bit. If I lower it too much, I'll start to lose the match. If I increase it too much, it becomes insensitive after a while. So I'm going to try and find that minimum where it just starts to depart and get it to match there. So I've now interpreted a combination of connected water, in-place water volume, and an aquifer productivity index that connects it to the reservoir. And that interprets the amount of energy that was available in this system that caused that diagnostic. So these are the sort of things that we can include in the modeling, in the type curve modeling, to try and get a better match of the data and a better understanding of what's going on. Okay, so that's material balance diagnostics. Another area that's of interest is productivity diagnostics. Now, balance diagnostics, as I mentioned, are long-term diffusive effects. Productivity diagnostics are usually going to be short-term, sometimes not, but usually going to be short-term and much more obvious effects. Okay? A material balance diagnostic is something that may take a long time to develop and may not be immediately obvious. A productivity diagnostic is something that's usually going to be very obvious. It's just our job to try and figure out what it is that's causing it. Okay, this is stuff that happens happens right near the well or in the wellbore. Material balance stuff happens far field, way out by the reservoir. It's a quieter signal. This is a pretty loud signal. So again, here's our production type curve. And the sorts of things that we are interested in here is a well cleaning up. That's usually a pretty obvious signal. When a well is cleaning up, the Q over delta P, well, the production rate might be increasing and the flowing pressures might be increasing at the same time. Any single phase type curve will illustrate pretty quickly that that's impossible. That can't happen. The reason why that happens is because when the well's cleaning up, there's relative permeability issues as completion fluids are being produced. And we're not modeling those things with these very simple type curves. The simple type curves assume single phase. So this is not going to match onto this. So that's our diagnostic. We can't really do any of that until that data starts to peak and the cleanup issues are resolved and now it matches on top of the type curve. That's the part where we need to focus on matching, and that's the part where we need to extract our reservoir parameters. And there's not too much we can do about this part. So that one you'll see quite often early time, particularly on wells that have large hydraulic fractures where you've pumped a lot of fluid into the reservoir and a lot of that fluid has to clean up. Liquid loading is another very common one that we'll see, especially in low-rate wells, like tight gas wells and conventional gas wells. And in liquid loading, we get a fall-off that actually looks very similar to interference, but it's caused by something completely different. Causes liquid loading effect is basically a buildup of water or condensate or whatever it is at the bottom of the well, and it just additional pressure loss that starts to increase with time. And that additional pressure loss causes that fall-off in either rates or pressures, and gives you that signature. So this one we can usually identify if we have enough information and we know the wellbore tubulars and we understand what's going on there. Some other things that are commonly seen is if you get parallel trends in the data, see that quite a lot. That could mean that something at some point in time, something's happened. So the operator has gone in and done a workover or changed up the tubing. There's some shift in productivity, step change in productivity because of something that happened. Remember, a simple change in flowing pressure, step change, like putting a well on compression, shouldn't cause this. Because when I change the Q over delta P, or both the production rate and the flowing pressure, the net effect is that the normalized rate didn't change if it's just a response to a change in back pressure in the system. However, if I physically changed the productivity of the system by recompleting the well and adding more perforations, or re-stimulating the well, or putting in a new tubing string, I will actually get shifts in the trends of these things, and they're very easy to recognize. The final one that's shown on here is an increasing damage. This one is notoriously difficult to identify because it's something that happens slowly over time, and so it has the same sort of time scale as a material balance effect. So we often mistake it for a material balance effect. In other words, we may often see this as early depletion and mistake an increasing damage for a depleting well, when in fact it's not. It's still got lots of reservoir pressure, but it's just had a slow accumulation of damage skin through time. So actually, let me start by showing an example of that exact thing. High-pressure, high-temperature gas condensate reservoir in the Gulf, similar to the other one we test. This one's even higher, much higher deliverability, produces a lot of condensate yield, a little bit of water, and the pressures are extraordinarily high. I mean, we're talking about 11,000 psi flowing pressure, 17,000 psi initial pressure, in fact, almost 18,000 psi of initial pressure. So an extraordinarily overpressured reservoir, probably psi per foot of pressure gradient, hydrostatic gradient. So we're looking at a very high overpressured reservoir. When we analyze the data in this well, this is the production data and flowing pressure data on the Blassingame type curve, the diagnostic would tend to indicate that we have a fairly well-behaved boundary dominated flow volumetric depleting system. However, I talked about this a little bit earlier, and that is the static pressure comparison to the flowing material balance analysis. And remember, I said earlier that we could sometimes see divergence between static pressures, which are shown here, and flowing material balance, which is shown there. All other things being equal, we would expect these to be the same. And the reason why they're not the same in this case is because we actually have a larger reservoir, but we have a declining productivity in the well. What we really should have in this case is an interpretation that looks like that. And now the shape of the data, the flowing data would indicate that the gas in place is much smaller than that. And that's because there's a whole bunch of accumulating damage that occurs through time. And we suspect that because this is so highly overpressured, that the reason for this is a compaction effect or pressure-dependent permeability in this well. If we now look at the productivity index of this one, we can see very clearly that the productivity index is a strongly decreasing function of time if we model it with the static pressures. Okay, so our interpretations sort of vary depending on whether we believe the static pressures or whether we believe the flowing pressures. Well, in this sort of situation, you have to believe the static pressures. And unless you think there's some error with the gauge, if the data is real, then you have to believe that that reservoir pressure is there, which means that the volume has to be there as well. In the flowing situation, there could be lots of different factors that cause that flowing data or flowing pressure to drop, accumulating skin damage, pressure-dependent permeability, all these things I talked about before, and that's why they don't match each other. So one final thing, we'll do a quick history match of the data. If we do the history match of the production data and ignore the shut-in pressure, everything looks fine. But when we include the shut-in pressure, we can see immediately that there's a bust there. Because our model would predict that the average reservoir pressure during that buildup would be in the region of 13,000 psi, whereas the actual pressure is more like 15,000 psi. So in order to establish a changing or accumulation of damage or changing skin through time, you have to have buildup pressure. That's kind of the key thing that we're seeing here. And we've seen this in more than one well. We've seen this in other overpressured systems and other reservoirs. But it doesn't become obvious. If I didn't have this data, I wouldn't have been able to spot that. So the diagnostic, in this case, requires the presence of a buildup pressure. If I didn't have that, I wouldn't have been able to make that conclusion. And I would have interpreted the wrong volume in place for this reservoir. So that's the increasing damage. Let's take a look, get a liquid loading example. Actually, to do that, I'm going to open a different file here. Sorry, that's not the one. Okay, this is the example I want to show. This is a tight gas well in onshore North America, normally pressured, low deliverability. There are literally thousands and thousands and thousands of wells like this. And so there's lots of data that have this sort of appearance to it. The liquid loading is actually, you don't even really need to do the type curve diagnostic. You can see immediately from the sawtooth pattern of the production rates that this well is producing in an unstable manner. In other words, we have high production rates and then they drop and then it probably pushes out a slug of fluid and then it continues in that pattern. So that sort of thing, any operations person will know what that is immediately, and we can see that. But I want to show you what kind of impact that has on the type curve analysis if you don't properly account for it. So this is the data, face value, no filtering, nothing taken out, and that's the interpretation that we get. I've purposely matched it here in such a way that it shows the liquid loading diagnostic very clearly. But if you were and didn't have a lot of experience and you came in and matched this, you might be tempted to try and match that unit slope over here and say that that's boundary dominated flow, and that would be a mistake because this data is due entirely to that drop off in the data is due to liquid loading. So it's the reduction in productivity because of that increasing column of liquid inside the wellbore that's causing this behavior. It has nothing to do with seeing the boundaries in the reservoir. They're two totally different things, but they look similar on these plots. So that's why I bring it up as an important diagnostic. Now, there's a couple of things you can do about this. Both of them involve filtering the data. One thought is that you would just go through and do a filter, and I call this the eyeball data trend. In other words, I'm going to draw some sort of line through the middle of this. And we can do this systematically. You can do it manually, or you can run what we call a median filter. And a median filter goes through, finds that central trend, and eliminates all the scatter above and below that data. The other way to do this is to go through and pick out all the data points that have fallen below critical liquid lift velocity. And there's an easy way to calculate that velocity using the Turner or the Coleman correlation. And once we've done that, we can eliminate those data points. Both of those methods involve filtering the data, and I used the term earlier on reservoir signal extraction. Both of those involve a reservoir signal extraction. So what I'm trying to do is get rid of all the noise that's in here that's messing up my interpretation and be left with something that's going to show me the true nature of the reservoir. Just to be clear, this is a subjective procedure. Different people might want to filter it in different ways. So there may be some biases built in there. It's not always going to be an exacting kind of thing. But we all know production data analysis is a subjective procedure. It's not always going to be to the third decimal place every time. There's going to be some flexibility and that sort of thing built in. So this is the final result after we've done what I'm going to call the clean type curve analysis. I've extracted what I think is the reservoir part. I've eliminated all the noise that was in there. And what we see is there is actually, it looks like a little bit of a downturn in the data that would indicate the beginnings of boundary dominated flow, 1.2 BCF. If you hadn't done that analysis, I don't think that you would see that because there's too much sort of noise and stuff built in there. So you can see why we're using the term reservoir signal extraction. We're hoping that there's something buried in there in terms of a reservoir signal. If we eliminate all the outliers and the noise operational problems that are in there, maybe we can see what's going on in the reservoir. That's the idea. Okay, so that's liquid loading. The productivity shifts are changes in the slope, same slope but offset in different places in the data. I won't show any examples for that, but it's pretty obvious in the data when you see that. The next section is transient flow diagnostics. And productivity diagnostics are things that happen because of operational phenomenon or the stuff that happens inside, dynamics that happen inside the wellbore or near the wellbore. Transient diagnostics are things that happen early in time. However, with the advent of very, very low permeability reservoirs, they may actually be things that happen it may take a long time